Good evening, everyone. Mr. Keitel here. I am going to film a bit of tomorrow's AP lecture. I guess it's today's lecture. It's pretty late. It's already Wednesday here. I have an unexpected personal day that I need to take tomorrow to handle something that's happening here at the house. Kind of family thing. Everyone's okay, but unfortunately, there's no way I'm going to be able to come in. So I've already sent out a message through Infinite Campus and Google Classroom. So hopefully you see those. The way this is going to work is AP is in C block, so you're just going to head home early. If you're in the school, group 2 is in the building, you're just going to head out to transition early. You're not going to show up to the classroom. If you are group 1 and you're remote, you're just going to do this from home instead of coming in. So no one show up to the Zoom meet, no one show up to the classroom. You'll find these slides that I'm looking at posted on Google Classroom, and that's where actually you probably already know that because this is where that video is going to get posted to. Okay, so let's go ahead and take a look at what we're doing today. Okay, it's not the worst day in the world for me to be out. The lesson that we were going to do today is practicing one-dimensional kinematics. Just like on problem set 3, that's what you're working on here. If anything we do here is not enough, we're in chapter 2, 2.5 and 2.6 specifically. Okay, this is one-dimensional motion, and we're using kinematic equations to make predictions. So there's remediation there. You can still email me. You can still shoot me messages on Google Classroom. You can reach out to classmates on Google Classroom too. So, or if you have people in class that you want to meet up with, you can work through this together. Okay, this isn't for points. Problem set 3 is for points. This is supposed to be practice. It's unfortunate that I'm not there to answer questions as we go through this together, but you still can get questions to me, like we said, through email or Google Classroom. So let's go ahead and get started. And this is what we're going to do. It's a 5-part problem that is going to take up all of these slides here. Okay, but it's going to be good. It's like repetitive, rapid fire practice. Okay? A 60-gram tennis ball is fired from a device, think like potato cannon. Okay, we're going to say the barrel is 1.5 meters long. Okay, it begins at the beginning of the barrel. There's a word for the breech is the end of the barrel where the ball goes in, and the muzzle is the end of the barrel that the ball comes out of. Okay, so the barrel's gonna be 1.5 meters long. It is pointing straight up. Okay, and it leaves the muzzle at 12 meters per second. What is the acceleration on the ball while it's in the potato cannon here? We're going to calculate the time it takes for the ball to reach its maximum height, okay, from the moment it leaves the device, so we're not counting the time in the device. We're going to calculate the maximum height above the ground, the total time spent in the air, okay, while it's in the device. That does not count as being in the air. Okay, and we're going to look at the velocity of when it hits the ground. Okay. We're going to ignore motion left and right, as we're going to see when we meet up with you next and we do two-dimensional kinematics. That's totally fair. We get to completely separate the vertical and horizontal motions because, in fact, they are separate. We can superimpose them on top of each other, but it's perfectly valid to look at one at a time. So we're only looking at vertical motion here, and also, like everything else in this, we're ignoring air resistance, we're ignoring air friction. So consider pausing this video right now, working through all of these without using the slides. Consider doing this whole thing first and see what you get. If you don't feel like doing that, because hey, Geidel, that's what we're doing in problem set 3. It's on our own and we work through it. We don't find out if we did it right till the end. Okay. At least consider going section by section. Right? Do part A, check yourself. Do part B, check yourself. Okay? Do not just go, oh, I'll just watch it. Oh, I'll just flip through the slides. Yeah, that's totally what I would have done. Okay? It's easy to say when you are following along. It's kind of like how It's easier to remember the words to a song when you're singing along with it, and then the song's not there and you try to sing it and you'll find you don't know any of the words. Okay, so try these first. Okay, really consider trying these first, at least part by part. It might, if you just kind of go through it and watch my logic, it might make lots of sense. It should, but that doesn't mean it's gonna come to your forefront of your brain when you sit down and try to do these by yourself. So try them first. All right, let's do part A. The acceleration on the ball while it's being fired. So while it's in the barrel. To find acceleration, we have a definition of acceleration. We know it's a change in velocity over time. Okay, so maybe you tried, since you tried these before you watch this, maybe you tried the definition of acceleration, change in velocity over time. We have a change of acceleration. We go from 0 meters per second to 12 meters per second. What's the problem here? Take a sip of coffee. Make you even think about it if you haven't yet. Sorry for slurping in your ear. Okay, we don't have time. We don't have a delta time. We don't know how long it was in the barrel for. Okay, so let's break out our fancy kinematics equations. We are in unit 1.2 here. Okay, so kinematics. Okay, we're going to do the chart. I like to put the axes that I'm doing there. I'm going to use the math class convention of up and down is positive, negative, y. And the part of the motion I'm going to look at is from the moment it begins to move, right? Basically from breech to muzzle, through the barrel, from the moment it starts moving to the moment it leaves the device. And let's start going through here. Hey, initial velocity. We were given that in the problem. It begins at rest, okay, 0 meters per second. Final velocity. Right? Well, since we always include, this is, hopefully by the end of this you'll see how beneficial it is to be very specific about what part of the motion you're looking at. Okay, so I spell it out here. I know in this case, final is as it leaves the muzzle. That is also given to us 12 meters per second. Okay, delta y, okay, change in y position. Do we have that? Yeah. Okay. We know that the barrel is 1.5 meters long, so by the time it leaves the device, it is 1.5 meters taller than, further in the y direction than it was. And actually here we've kind of already implicitly picked our coordinate system. Don't think I forgot to do that, okay? I wanted to see show you how you could kind of do this a little bit into your problem. And again, it doesn't matter what we pick, okay? We kind of alluded to it when we said we were going to use math class as y-axis there, okay, where up is positive and down is negative. And that's actually what we're going with. Okay? The the velocity rather, that's a vector. It has direction. I typed it in as a positive number. So right there, I'm assuming up is positive. That's fine. The displacement's in the same direction, so they should have the same sign. Which is all good. Here I made it explicit. We have our coordinate system officially declared now. And it's good to do that first, but if you find yourself writing numbers down and you don't think about the coordinate system, that's okay. Just make sure that vectors that point in opposite direction have opposite signs. Vectors that point in the same direction should have the same sign. Okay? Your coordinate system should be consistent throughout, but we kind of implicitly declared it when I put a positive number there for that first vector. That was non-zero. Okay? I don't have the acceleration, but that's what I'm looking for. So I'm going to circle it in my little kinematics chart. Okay, do I have the time? Well, no. That's why we couldn't use delta v over t for a, right, for acceleration. So I actually don't care about time. But I have 3 variables. I'm looking for a 4th. I now have enough information to start shopping for a formula. And this is right out of our kinematics section of our fact sheet. So which kinematic equation has the 3 things I have, and it also better include the thing I'm looking for, otherwise I can't solve for it. There you go. Okay, it that delta x in there is just a displacement. It's okay. We're working with y's this time. Let's we'll change it to a y there. Right? But yes, this has everything where we have a final velocity, we have an initial velocity, we have an acceleration, we have it, or so, yeah, no, so we don't have an acceleration, but we're looking for it, so it's good that it's there, and we have a displacement. Let's rearrange. It's just some algebra. Right? I go ahead and plug things in, drag your units around as long as you can stand, okay, because whatever you do to the numbers, you'll do to the units, and the units should always make sense, should always be consistent. You should never find yourself adding and subtracting things with different units. You can't add apples to oranges, okay? And when you have an expression, say we're looking for acceleration here, I better get units of acceleration. So let's see here. More math. I get 48 meters per second squared, which is a lot of acceleration. Okay? It's pointing up. I'm getting faster and faster in the upwards direction, so I'm going to make that a positive number 2. Acceleration is also a vector. Alright. There's the acceleration on the ball while being fired. Part A is done. Look at B. Calculate the time it takes for the ball to reach its maximum height from the moment it leaves the device. Okay, so we're going to stick with our coordinate system here. Up's positive. This will be the coordinate system we're going to use throughout this problem. And again, you could have down be positive. That's okay. You just got to be consistent. I'll be doing up as positive. In my kinematics chart, I'm going to be specific about the motion I'm looking for here. So this is actually a different section of motion. It's a different kinematics chart. This one's from the moment the ball leaves the barrel to its maximum height, its peak. So now that 12 meters per second, the kind of exit velocity or muzzle velocity with this tennis ball cannon here, it was the final velocity in the prior portion. But in this section of motion, it becomes the initial velocity, right? So my new time frame is beginning right where the original time frame end. And they overlap by one moment, that moment of exiting the device here. So positive 12 meters per second, because it's moving up at 12 meters per second. And up is positive in my coordinate system here. So what's my final velocity? This is a common trick we're going to pull, and I mean we picked our time frame's ending at the peak because we're looking for the time it takes to reach the peak, maximum height, right? But we know a bit of information about an object at the peak of its trajectory, right? It's for one moment at the maximum height there before it starts falling back down, it ceases moving altogether, and it's actually at rest for one instant at the peak of motion. And so 0 meters per second is our final velocity for this section of motion. Okay, what's the displacement? We don't know. Do we care? We know that we are talking about the maximum height. If we had that maximum height, we might be able to do some math, some physics, some kinematics, and use that maximum height to find a time. Let's say for now that we don't care. Okay? We don't care what it is, and we're going to move on to acceleration. Okay? Because what we're actually looking for is the time it takes. And yes, we could find the maximum height and use that to find the time it takes to get there. But these kinematics equations are actually pretty smart. And if we're very disciplined with our positives and negatives, and we're very disciplined about knowing which section of motion we're speaking about, they're actually very powerful. Let's go ahead and let's try to do this in one step. Let's calculate the time it takes. I'm going to say we don't care about the displacement. Okay, but I am going to circle time in my kinematics chart there because that's what part B is looking for, the time it takes to go from the barrel to the peak. Okay, so the acceleration, what is the acceleration? When we get to dynamics in Unit 2, we're going to talk about forces, things Objects accelerate when they're pushed or pulled by forces. Hey, we talked a little bit about this so far, but pretty much we've just kept to kinematics, which doesn't really care why things move, just trying to describe how they move and predict where they'll go and when. Hey, but we know what's causing the acceleration. Okay? In free fall motion, okay, and this is free fall motion because the only thing pushing or pulling on it is gravity. Okay, my acceleration in my vertical direction is 10 meters per second per second, 10 meters per second squared. Okay, gravity, that's acceleration due to gravity. You could do 9.8 meters per second squared if you'd like. And again, remember on the AP 1 exam, they'll include both. They'll consider both in the answer keys. Okay? So that's actually our acceleration. Now, I'm going to make it negative because up is positive and gravity pulls down. Okay? That's kind of like my physics reason, right? Gravity pulls down and up is positive. Mathematically, right, let's think about it. I know when I throw something up into the air, it's going to slow down, and that means velocity and acceleration are in opposite directions. Well, I already said my velocity is positive, acceleration better be negative. And if you were in a coordinate system where down was positive, that would be 10, but then that would be negative because, sorry, that would be positive 10, but that would be negative 12 because they're pointing in different directions. They need to have different signs. So I'm running with our math class favorite here, where up is positive. That means gravity pulling down is a negative acceleration, which ought to make sense, both mathematically and physically, given our coordinate system. Okay, we have 3 variables. That's okay that we don't have a fourth. We're looking for the fifth. That's enough for us to shop for an equation. So which kinematics equation, has acceleration, final velocity, initial velocity, and includes time so that we can solve for it? Did you pick this one? I did. Okay, let's take a look at it here. Let's rearrange for the thing we want. Do some algebra. Okay, and let's substitute in. I like to be mindful of units. Right? I get a meter per second divided by a meters per second squared. So remember how to divide fractions. Stay, change, flip. When I flip this, the meters go to the denominator and cancel those meters. And when I flip this, the seconds squared come up top. One of them gets canceled there, and I'm left with seconds as my unit, which makes sense. Okay, so hopefully you got 1.2 seconds from the leaving the muzzle of the device to reaching the peak of its trajectory. 1.2 seconds. Now, how high did it get above the ground? It's at its peak, 1.2 seconds after leaving the muzzle there. It's at its peak. How high is it above the ground? Well, we have our coordinate system. That's always step 1. Step 2 is your chart. Okay. Now, because I'm looking at the same section of motion, I get to run with my same chart, and all those variables are still relevant there. Just now, I do care about the displacement. Okay. Now I want to know what this tells me is how far in the y-axis this object went from leaving the barrel to hitting its peak. So let's shop for an equation. Now you might be tempted to use one with time, and you can. We worked hard for that time value. And there may be problems where you have to use the time. But if there's the option to, I always try to use the information given in the problem as much as possible. It's not that I think this is wrong. I'm pretty sure, I wish that would go away. I'm pretty sure it's right. That 1.2 seconds is good and we worked hard for it. But, maybe the person grading or reading your work rounds differently, or I guess that's really the big thing is what if we rounded too aggressively and the answer we end up with doesn't match what we were expecting. And this is less about physics and more about being a student. I try to use the information provided in the question as much as possible. It's just me. You could pick an equation that, as long as it had displacement in it, because we want displacement, you could use something with time in it and use your 1.2 seconds for that. But there is an option that does not require the value we calculated and uses only things provided by the problem. So I'm gonna chicken out and go with that one. Okay, that's just personal preference there. It doesn't matter the delta x is delta y because we're looking at the vertical position. Displacement's displacement. So let's rearrange for displacement. More algebra. Do, 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 do. We'll substitute in. Okay. Being careful not to lose track of negative signs. They don't. They do just here. They indicate directions, but directions can be important. And as we do math, they will affect not only the direction of your answer, but the magnitude of your answer. So don't goof up a negative sign. And what's worse is it won't always change the magnitude of your answer, which is unfortunate because we build bad habits. Sometimes you can forget about negative signs and kind of physics it out and reason it out and slap the appropriate sign on it at the end. But sometimes it will even change the number, the magnitude of your answer, not just the direction. So get in the habit of being consistent with your signs there. Here, my negatives cancel out, and I get a positive 7.2 meters, which makes sense because I'm moving upwards. In this coordinate system, upwards is positive. I would expect a positive displacement. So we're all done, right? We're 7.2 meters above the ground. Psych. No, we're not. Okay, why? Right, we want the above the ground height. And our handy dandy kinematics chart here reminds us that this section of motion, these numbers are only good for leaving the barrel to the peak. So this displacement is the height above the barrel, right? Because the motion in this chart began at the muzzle, so that displacement is from the muzzle. So we have to add on the height of the barrel, okay? The chart we just did is good from here to here. This is the chart we just did. Don't forget that it started 1.5, it started this section of motion 1.5 meters from the ground. Okay? So to get our height above the ground, we just add the barrel onto it. We should have 8.7 meters. Let's do part D, the total time spent in the air. And here I make it clear that being in the device is not part of being in the air. We're talking from muzzle to ground. So, how many kinematics charts do we need here? You might be tempted to break the motion into two chunks, which you can. I mean, we have a time for here, right? We just found that was 1.2 seconds in an earlier part. So if we did one kinematics chart for this side, we could add them together. We can do that. That would work. And then there will be problems where that's the only way to do it. But here, and actually I take it back. It's not really extra work because we already have the time for that leg. But I do try to avoid reusing answers from prior parts. There will be problems where you have to. I can think of a way where we don't have to. Let's try it in one chart. Okay? So I'm going to make clear my range of motion here is the entire range of motion here from the moment the ball leaves the barrel until it strikes the ground, the entire time spent in the air, which I could have put that here, time spent in the air, but I like being specific. I like to make clear the initials, velocity initial, position initial, everything at the beginning of the motion, and make clear everything at the end of the motion. V final, Y final, okay, is when it strikes the ground. So my initial velocity is still positive 12 because I'm beginning as the ball leaves the muzzle of the barrel here. Okay, V final. What's V final? Do we know? Nope. Don't care either. Okay, it's going fast, right? Because it's going to go up. It'll come to a stop, and then it'll speed back up, and it'll hit the ground with some negative velocity, some downward velocity, and I don't know what it is, and I don't even need it here. What's my displacement? Well, do I need to know the whole track? Maybe I add the maximum height, and then I know it's the same distance back to the muzzle and then the barrel. No, remember, okay? It's negative 1.5 meters. Displacement doesn't care about the path. If you find yourself, okay, I know that that's, what was it, 7 meters, and this is 8.7 meters, and sorry, it was 7.2 or whatever. Hey, we don't care about total distance. This is change in position. This is displacement. Distances do not go here, only displacements. And in this section of motion, from the moment I leave the barrel till the moment I hit the ground, I end up 1.5 meters lower than when I started. These equations are powerful. Let them do their thing. Okay, there's no need to chunk this motion up. Okay, displacement's a vector, just like velocity, and while my initial velocity was upwards, my final displacement is I'm lower. When I do final position minus initial position, I get a negative because I'm lower. Right? You can imagine y equals 0 is here. Alright? Y equals 1.5 meters there. Okay, that's why we do final position minus initial position. 0 minus 1.5. That's my displacement. Okay, so I'm 1.5 meters lower than when I began. Acceleration due to gravity is still down, still free fall. Okay, gravity's the only thing pushing or pulling on this. Once it leaves the barrel, obviously the device, the potato cannon, if you will, is obviously pushing and pulling on it to get it to move. It accelerates it at 48 meters per second squared, like we saw. It actually accelerates it more than that, but then gravity's fighting it. The net acceleration, a concept we'll look at in Unit 2, the net acceleration is 48 meters per second squared. Okay, so here we go. And time, we don't know it because we're looking for it. If we knew it, we'd be done with Part D. So there we go. Hopefully this makes sense. And we're going to do this in one smooth kinematics chart here. Okay, which equation will accommodate us here? Better not have V final in it because we don't know it and don't care. This equation has things we know and the thing we're looking for. Okay? So, and actually this is in the summer work, in the summer math review, this was a task that you had to do. Okay, how do we solve that for t? You might, okay, I'll, factor out a t and divide it over, but there's a t and a t squared. You're still going to have a t left over. You cannot get this into t equals blah, 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 blah without pulling this trick. I don't know if trick's the right word for it, but this is a polynomial. Right? It's a quadratic equation. We're going to use the quadratic equation to solve it. You will not be able to isolate it otherwise. Okay? Let's dust off the quadratic formula here. Right? If I have a polynomial in the shape of that, okay, I'm actually going to make some substitutions here so I don't have to drag around everything right away. Okay, right, that's the typed into Google slide version of the quadratic formula there. Right? T equals negative b plus or minus b squared minus 4ac square root, right? Remember we raised to the 1/2 to square root. All over 2 times a. Not a acceleration, a the coefficient of the squared term. So that's why we made that substitution there. Okay? In math class we said 0 equals ax squared plus bx plus c. And so that's why when you see I define c, I define it as the negative delta y there. Okay? Remember this from math? We're going to need this couple, here and there. Okay? So what I go ahead and I plug my physics back into my math equation there. So this is what it looks like with the physics terms in. A, B, and C I plugged back in. It's messy, but paper's cheap and space on a Google Doc is cheap and use as much room as you need. Get it right. Mhm. I plug in the numbers. I drag units with me. Right? The discriminant is a positive number, which means there's two real solutions, if you remember that from math class. Keep doing some math. End up with 1.2 seconds plus 1.3 seconds, or 1.2 seconds minus 1.3 seconds, okay, which results in the time is either 2.52 seconds or negative 1.2 seconds. Both of those would solve this, right? But and both of them are legal mathematical answers, but in physics we're not going to have negative time. Time is not a vector. Time's a scalar. A negative time doesn't make sense here. Okay, so that's actually our answer. Okay, interesting tidbit. Okay, let's go back up real quick to my picture of the scenario. Okay, this was time equals 0. What that negative 1.2 seconds represents is if I traced this trajectory back in time, that's negative 1.2 seconds. Now remember, so it took 1.2 seconds, or sorry, 0.12 seconds to fire through the cannon? No. The accelerations were quite different here, okay? But if we trace this trajectory back in time, that's where negative 0.12 seconds would land. Okay? It's the other answer, the other time that the displacement, or that the polynomial sums up to 0. Alright, so that's part D. The total time spent in the air, it's at 2.5, about 2.5 seconds from muzzle to ground. Part E. What is the velocity when the ball strikes the ground? Okay, we can use the same chart here. From the moment the ball leaves the barrel until the moment it strikes the ground. Well, striking the ground is what we're looking at, so all of a sudden we do care about V final now. Okay? Here's an equation that has the things we need. I even managed to avoid using generated information, although I'm sure it's sound, I'm sure it's good, but we're going to, I prefer, as I mentioned, using stuff given to me because it's rounded the way the author wants it rounded, and it looks, and just, it's a student thing, it's not a physics thing. So let's go ahead and solve. Okay, my units are consistent, okay. Velocity is meters per second, so velocity squared better be meters squared per second squared, right? I'm adding like units, it all works out. I'm being diligent and careful about my positive and negative signs. Here's an example where I bet if you goofed up, if you forgot the sign on the negative 10 or the negative 1.5, you really would change not just getting a different sign, but you would really change the magnitude of your answer too. Okay, so I take the square root of both sides. Remember, raising to the half power is equivalent to a square root. It's just easier to write in Google Slides. And when I take square roots, there's actually two answers, positive or negative. Okay. Here I'm going to invoke a little physics and say I know it's moving down. I'm going to run with the negative answer. Okay. So that is the practice problem there. Okay. Hopefully you were able to try these first, and this was helped you iron out some kinks you had. If you did just kind of follow along, that's okay. You get more practice on problem set 3, which you guys have already. It's due Friday by class time start. Okay? thank you for understanding that I was not able to attend today. I'm embarrassed and mortified and angry because we're just getting started, and honestly, I'm just angry about the whole hybrid learning thing in general, and part of why I can't come in has to do with my kids and the fact that they're remote. And I very much look forward to maybe this all getting back to normal soon here. So, again, apologies and thank yous. And email me and post on Google Classroom if you have any questions. Good luck, and I will see you guys soon. Thank you. Bye.